Hey guys, welcome to another episode of Genuine Chit-Chat. This week, I'm joined once again by my friend Josh. Now, as any of you regular listeners should know, usually when Josh comes a-knocking, it's time for some science, because Josh is an incredibly intelligent individual. He's basically training at the moment to become a science teacher. He has degrees in marine biology, I believe, college qualifications of science, so he's a very science know-how kind of guy. So I like to have these episodes every now and then just to talk about essentially generally everyday things that we kind of know about and see but maybe don't fully understand, and try and explain them in an easy to digest manner, because I'm not smart enough to understand all these things. So I thought it'd be quite nice to have Josh talk them to me in an easy to understand way, and then me maybe sort of say them again in an even more simpler way, so hopefully the majority of people listening would be able to understand all these things. So that's generally what Science But Simple is all about for anyone who hasn't tuned in before. Now, in this episode, it's about the correct scientific terminology. We talk about sort of weight and mass and theories and hypothesis and that sort of thing. We also talk about black holes, especially because if anyone's been paying attention to the news recently, there was the first image of the black hole, essentially. And we talk about that a bit. We talk about black holes in general and that sort of thing. And Freudian slips come up at one point as well, because I mentioned them. So if you want to know what a Freudian slip is and you can't be bothered to Google it, then you can find out here as well. So lots of different things in this episode. Now, I did say in the episode, I believe, that it's probably worth, if you haven't already, going back and listening to number 2 of Science But Simple, which is actually the 12th episode of Genuine Chit-Chat, only because it has a sort of general overview of gravity, orbit, the sun, the moon, that sort of thing. You don't have to do that at all. It's completely optional. Just if you're not that scientifically literate, then it may be worth going back there and listening to that one just to get a sort of general overview before going into this one, because especially at the end, we get into slightly more details about it. So it's slightly less Science But Simple, but it is still quite easy to understand generally. Anyway, I'm going to stop rambling and half talking about science, and I'm going to let Josh essentially get into it. But before we get started, there'll be a quick promo for the Millennial Nerds podcast, and then we'll get straight on into it, and then I'll be back at the end, as I always am, to talk about what's coming up and all those usual things. So, like, subscribe, share, follow, blah, 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 usual things. Thanks for listening, guys. I really appreciate it, and I'll talk to you all at the end.
Hello, my name is Scott Cooper. I'm the host of the Millennial Nerds podcast. I get to talk to our community about what we love doing, from the products that we make, to the people behind them, to the opinions, to the streamers, to the gamers, to the YouTubers, whatever you want to call yourself. This is our story, and this is your podcast. Listen to me on iTunes and Spotify, or find me on Facebook at Millennial Nerds.
Welcome to Genuine Chit-Chat, where we have honest conversations with interesting people. And I'm your host, Mike Burton. Let's just jump right into it. Hello guys, welcome once again for another episode of Science But Simple, the mini-series on Genuine Chit-Chat. I'm sure I've rambled on for far too much time in the intro talking about it, so we'll kind of get straight into it. As always, I am joined by the powerful Josh, and we're going to talk about some science today.
Hello.
You're not allowed to say hello, Josh. You're allowed to speak when spoken to.
I'll leave then.
Good. So today we're going to talk about a couple of things, and we're going to talk about sort of misconceptions of certain words, phrasing and things, and then we're going to kind of go on a little tangent about other stuff, but we'll kind of get onto that a bit later. I may have spoken about it in the intro, so we don't want to bore you and repeat myself. So we're just going to get straight on into it. So one of the things, Josh, one of the big misconceptions is to do with sort of weight and mass, but also theories and hypotheses and all these sorts of words that we use in our day-to-day. But as you often correct me, I use them wrongly, and I should be fairly well known about science to some degree, but clearly I'm not. So I thought we could, chat about some of those misconceptions. So one thing we were talking about earlier in the kitchen, and I was talking about something being a theory, and I think you corrected me, being a hypothesis. So if we just use that as a sort of jumping off point.
Yeah, basically there's just a lot of difference in the way that language is used scientifically and the way that language is used in just your everyday casual person-to-person language. Weight being a massive example that probably is used daily. But to start on the science front of theory and hypothesis, one of the most triggering things you can probably say to a scientist, like, oh, it's just a theory. And it's like, quietly seethe.
Evolution is just a theory.
So to put it to definitions, in everyday language, you might say, oh, I've got a theory that like this and that will happen and this and that. That's perfectly fine. But whenever you're looking at people in science, whether reading an article or anything like that, or talking about a full scientific principle, a theory is a well understood thing, or thought to be well understood thing, that is backed up by a significant amount of evidence. One of the big examples of it being said about just a theory is often evolution, and essentially people contest it, saying either it hasn't been observed, which it has, or like it's just a theory because there's no other evidence. And yes, if someone were to come along with a significant piece of evidence that would discount previous evidence, then the theory would change. Scientific theory, science doesn't work in the way of proving things right. A lot of the way that science and hypotheses, which is like, hypothesis is the word that you probably use instead of how you use theory in regular language. So if you've got like an idea of, if you increase one thing, the other thing decreases, I'm going to test for that. That's your hypothesis.
So it's the initial the first thought of, this is the starting point, is the hypothesis.
Yes.
Yeah. Okay.
So with a hypothesis as the starting point, which is normally the way you probably use your everyday definition of theory, you then move into collecting evidence and sampling and scientific principle, and the scientific method, in which you don't prove things correct, you disprove things. So you can make inferences and relationships and ideas about correlation, but again, correlation does not mean causation. So just because people with a higher shoe size buy more ice cream, that doesn't mean that bigger shoe size you have, the more ice cream you buy. That's just like a random trend that's occurred. It's not one causing the other. So a lot of the time we're trying to find out and test something and say, okay, if this is true, then we'll see this in results from an experiment. Oh, wait, it's not shown that, so we can disprove that hypothesis, and we know that that's not what's going on. So you essentially say, these are all the things that could be happening, and start knocking them off one by one to say, no, that's not right, that's not right, that's not right, because there's evidence to show that that's not what's going on, because the expected results for if it were true aren't happening.
I see, yeah. And it's that thing of, that's what one of the things that people say about sort of more aligning with people who have religious ideology, obviously not all of them, but a lot of them saying things like, science acts like it has all the answers and things like that. When the answer is no, it's like the opposite. Like, science is saying, we literally have so little answers and we're so not sure of things. We have to basically just eliminate what they could be. And then when we're left with one, we're like, well, we'll just go with this for a while unless something else comes up to disprove it.
Yeah, I pretty much put it as almost like a curse of knowing. And the more you know, the more you realize you don't actually know. And then it's like, oh God. I just put my hands on my head like, oh God, I don't know what's going on. But that's like a big part of things. And in looking at the evolution side of things, which we probably could have an entire episode about, but we have, for example, a really good one is the fossil record of the horse. We have a fairly respectable fossil record of humans. We have now DNA to run off. We've literally observed one species diverging into different species based on conditions.
Oh, really?
The very fact of antibiotic resistance in bacteria is a form of evolution occurring right in front of us. So there's plenty of evidence to say this is what's going on. Mm-hmm. And there's so much that once you have enough evidence, something is then classed as a theory to then say, well, pretty much for as much evidence we've got, as far as our understanding is at the moment, we can pretty much treat this principle as fact until something comes along to improve the theory or change it significantly.
I see, right.
But science is always looking at being adaptable and saying, well, if something does come up in the future, then the theory has to change.
And just a quick thing, I've heard the term scientific method used quite a lot. When I was in Amsterdam last week, I went to a microbe museum called Micropia, and I recommend anyone who goes to the zoo in Amsterdam goes check that out. And in there, they mention the scientific method. Do you know off the top of your head what it is, essentially, or like a vague? Have
you heard of like the sort of little, I'm not sure what the soliloquy is, but a little phrase like science is a verb?
Kind of, yeah, I think so.
I mean, there's also like a social media page or something that's called that as well. But essentially, you talk about the scientific method as science isn't like a subject. Realistically, yes, you teach science taught, like I'm trained to be a science teacher with this currently. But that umbrella term for the subject is one thing, but science itself and people doing science, it is something it's a process of testing and hypothesizing, controlling variables and deciding things are going to change and making sure experimentally or observationally that you're able to produce evidence for something. It is about that idea of trying to find something to disprove. So you can say that's not the thing that's happening, throw that out the window, move on to the next thing. It's a continuous process that evolves as you go along.
Well, there was one, it's a vague anecdote because I can't remember what it was about, but there was one which was about a guy who, I can't remember what it was about specifically, but he had this theory, this hypothesis, and he came to it and he was like, this can't be true. He was like, it was like a math equation or something like that, and he was like, this can't be true. I've clearly done something wrong. And he spent like years and years and years of his life trying to be like, this clearly can't be right. Like, and he was like, he eventually got to a point where he was like, I've tried every experiment I can think of. He put it to the scientific community. Then they were all like, yeah, that can't be right at all. And then no one could disprove it. And then years later, he gets the Nobel Peace Prize. And that's a kind of good insight into what the world of science is like. It's once you've got your hypothesis, and even if you've solidified it a bit more with experiments, you then put it out to the world, and other scientists will try and work it out and things.
Which would, in what we would call it in terms of, especially when you start publishing literature and journals and all that sort of thing, is called peer review. So you basically say, here's what I've done, and subject it to the criticisms and observations of everybody else, laying bare your methods and results and everything for other people to look at and say, hang on a minute, what's going on here? This doesn't look quite right. And then other people can then emulate what you've done to see if what you have done is really producible, which then provides further evidence for, oh yes, then that original study is fine. There are cases where certain people have done one thing, produced some sort of literature from it, published, who said, hang on a minute, done it themselves, and got completely opposite results because they've changed something to improve that method, to isolate something more. And then it says, well, originally that's what happened, and then no.
Yeah.
So again, it's like that whole process of how you do things and how you manage what you're trying to disprove is that the whole principle of what people do.
I see. And are there any other, keeping in what we sort of started with, are there any other sort of scientific terminology or things like that spring to mind that people often mix up or confused?
Probably energy is one.
Right.
It's not like there's a different word to use instead. It's just like by technically how it's referred to in science, the way that we use it in everyday language is different. Again, I would, the one with theory and hypothesis I'd probably put as a little bit of a misconception, because it's like a lot of people misinterpret what scientists are saying when they use the word theory. But when it's stuff like energy, that's one thing. When you talk about weight, that's weight and mass. Well, when we refer to we're weighing ourselves, what you're really doing is massing yourselves. It's like mass yourself. It's like, can you mass this item? It's like in a speaking way, it sounds weird and it sounds wrong, which is why it doesn't sit right.
Yeah.
But what you're doing, because your scales, actually, no, this is another thing actually. So technically, when you put yourself on a set of bathroom scales, you are measuring your weight. I mean that in terms of the scientific meaning of the word.
Right.
You are measuring the force that you are exerting on the ground due to gravity.
Right.
What the scale does is the little calculation that converts that measurement of force into a mass by the strength of Earth's gravitational field.
Right.
And then give you the mass number from the weight that's being measured.
Right. So for people who are listening, to explain it in a slightly alternate way, if we use an example, if you use a different gravity, so if we say Earth's gravity is force of 1, if you use the moon or something, if you want to kind of elaborate more on how the difference in gravity can affect.
I can explain this. So for the sake of easy numbers, let's say that actually it is close enough to Earth's gravitational field strength, the strength of gravity, is 10 newtons per kilogram. It's actually like 9.82 or something, but we'll just round it to 10 for the purposes of this. If you put yourself on a set of scales and you weigh, for example, 70 kilograms, well, no, your mass is 70 kilograms. So this is how easy it is to get wrong. Or to mix up the language, at least. I wouldn't say wrong, but yeah. So if you have a mass of 70 kilograms, your weight on Earth is 700 newtons. And your bathroom scale is measuring 700 newtons, then doing a little calculation, dividing by 10, and showing you 70 kilograms. Mm-hmm. If you were to go onto the moon with the set of scales, same set of scales, because the set of scales is calibrated to Earth's gravitational field strength, if you then put yourself on that set of scales on the moon, it would show your mass to be about a sixth of what it would be on Earth, because the gravitational field strength is less, because it's measuring your weight and converting it into a relative mass to show you the mass based on Earth's gravity.
Right.
So if you were to set your bathroom scales to a different planet, your mass shown on the scale would change, but it hasn't actually changed because your mass is the same.
Yeah.
It's your weight that has changed.
Mm-hmm. Yeah. So the main, it's just between the mass and the weight is just, the mass is the one that doesn't change.
Mass does not change. Mass is the amount of stuff that you have.
Yep.
Weight is a force due to the effects of gravity.
Mm-hmm. Yeah, I see. So obviously it's that calculation of, you increase gravity and then your weight will in turn kind of go up because if the gravity is twice as strong as it is on Earth and you set on the scales that haven't changed, you would seem to be twice the weight.
For example, on Jupiter, you'd expect your weight to be 24 newtons per kilogram rather than 10.
I see. Yeah. Well, that makes sense. Yeah. So obviously that was one other thing which was with sort of weight and mass and things that people often sort of get wrong. As you say, when we say these misconceptions, this is more of just kind of people getting knowledge. Like it's very rare for people to be like actually annoyed that people say weight or mass or anything like that, or theory or hypothesis. That's just in the general public eye, it's just quite an interesting thing of the slight variation in terminology when you get into the scientific world and some of the confusion that can cause. Now, are there any other that spring to mind immediately?
One of them is heat.
Okay.
And I don't quite understand this one entirely. It's a bit a weird one to get your head around.
Yeah.
But essentially, heat is to do with internal thermal energy.
Yeah.
So it's correct to say, you're heating something, or it's like you are, or I'm going to heat something or heating something. That's perfectly fine as using it as a verb. But as a noun, heat, like you say, close the door, you're letting the heat out. No, what you're doing is letting the hot air out, because that heat's not changing. It's just that gas is moving from place to place,
right,
and redistributing itself to be kind of relatively equally distributed, which often means a lot of the hot air leaving and the cold air coming in. Right. But the actual heat itself, because it's internal thermal energy, isn't going anywhere, because it's essentially within the molecules of the gas.
Yeah.
So it's one of those weird things that, like, saying about heat being heat, the noun, we use it a lot, doesn't quite work. One of my essentially the lecturers / course leaders for my teaching course, who's a physics guy, actually ended up being my tutor during my first year of college, actually, which was a nice surprise when I went in and saw him. Basically says that he's changed his way even at home now, because he's a bit making sure that he's changing the way he's using them, in both for teaching us as teachers to be using it correctly, as well as to get himself used to it. Is that he doesn't say that. He doesn't say, I'll close the door, you're letting the heat out at home anymore with his family. He says, I'll close the door, you're letting the hot air out.
Right.
And he actually practices in using his own everyday language to be using it to be scientifically correct. Which some people might say sounds really sad or whatever, but it's like, really what you're doing is just trying to use your language properly.
It's stopping. I think the term for it is Freudian slips, if I'm correct. I do often get the term Freudian slip confused.
I thought that was like about like things that are innuendos and stuff.
Well,
I don't know.
the thing for a Freudian slip is one of two things. I think I'll double check it in a sec, but it's either you say something, your mouth basically says something that your brain wasn't thinking, or it's the opposite, where a Freudian slip saying like you look. Like, you look some. If I was going to say you look something today, and I was meant to say you look great today, but instead I accidentally say you look shit today, even though my brain, I was trying to say you look good, but I was actually thinking you look bad, and it slipped out. You know, Freudian slip. I will have to check that out.
Yeah, that's another one.
Just to be sure.
But yeah, so that's another. Heat's another example. So heat, weight theory. Energy is just because energy is essentially an accounting mechanism that is used in science. It's not like an actual thing. Energy really is like an abstract concept that we use. It's not like it's not actually really existent. We just see it as a potential for work to be done, which is another whole kettle of fish of terminology, which we're probably not getting into right now.
Yeah, it's maybe science, but simple. Yeah. That's the key thing. With Freudian slip was the latter of what I was saying, just to clarify to everyone. It was basically a slip of the tongue in which the word the speaker was subconsciously thinking about is substituted for what they meant to say. So I was thinking you look bad, I meant to tell you you look good, and I say you look bad. That's a Freudian slip. So yeah.
Okay. Oh yeah.
Wonderful. Aside from those ones, then, is there anything else, or do you want to get on to the next?
Off the top of my head right now, those like the main ones that are specific about the language that we're using.
Okay, no worries at all. Well, because we were speaking about weight, I think how this sort of conversation about the misconceptions in scientific language came about was we were talking, or I was talking about sort of the black hole thing, and we were talking about black holes in general, because obviously this podcast is going to be released this Sunday, so it will still be within a few weeks of it happening, of the image of the black hole.
Yes.
Which everyone's talking about a lot. And so obviously I don't know anything really about black holes except the vaguest of vague. And obviously I know you know quite a bit about it, but there's so much to actually know that it's incomprehensible for you to know everything. So I just thought we could have like a general chat about black holes and just a bit about why the image people have got is seen as important, or what it kind of is in a sense. So generally a black hole. So obviously I will say what I imagine most people think it is, and you can tell me that I'm wrong. Okay,
so you want to talk, and I'll be like...
just smiling and nodding your head and
smile and wave, boys. Smile and wave.
So essentially a black hole, what most people would assume it is basically it's a hole in space that is basically sucks things into it. You're shaking your head. It's a hole in space and it sucks things into it, and if you fall in it you get killed, or you go to a different dimension or a different universe or whatever. That's basically, people think it's a hole in something and things fall into it. So Josh, is it a hole?
It is bad juju. No. No, so for my understanding, and this may not be entirely correct, but I would assume a black hole to be a solid mass.
Right.
But it is probably infinitely, maybe not infinitely small, but it's incredibly small, at least for its mass. Again, we're using the right words here, mass. So you've set out the term, it's a Muse song for, supermassive black hole.
Yeah.
And supermassive black holes are often smaller than regular black holes.
Okay.
Because the amount of stuff that's there, because we said mass is the amount of stuff, the amount of material that is there, there's so much more, there's so much got the amount of the gravitational strength there is so much more that everything has collapsed to be much smaller.
Right.
And that in turn increases the gravitational field strength because it's to do with density.
Right. So supermassive black hole, the actual thing itself is actually smaller in size. Yes. However, its mass is greater and therefore it has a greater effect.
Because remember we were saying about mass, when we say supermassive, actually this is another quick misconception, isn't it, really? Yeah. Because when we say massive in everyday language, we think about size. What we're talking about in terms of black holes is mass, as in the amount of stuff. That doesn't necessarily take up more space. It might have more mass, but be smaller, which means that its density is much greater.
Yeah. Well, that conception comes about, I think, misusing terminology, probably because in general, if of the world we live in, without looking too deeply into sort of the periodic table or anything about science, essentially, just everyday life, when you see bigger things, generally speaking, they are heavier. Like, not all the time, because obviously,
in general,
that's why the thing is coming. You know, you see a whale that is a very large and very heavy being.
Compared to you, a whale is massive.
Exactly, in both the correct term and the incorrect term. However, one way of saying something would be, for example, let's use a balloon, for example. If we had a balloon that we could blow up in the size of this room, it would actually still weigh less than us, but it would be bigger than us.
So it'd have less mass than us.
Well, there we go.
And probably hence, because we're all both on Earth, way less as well.
Exactly. So it's one of those things where that's probably where
this is how pedantic you need to be with language.
Well, not only that, we got to be, I mean, this isn't even scratching the surface of how pedantic you need to be with science, because, you know, even the tiniest of nano measurements being off can completely disrupt an entire...
I guess pedantic is the wrong word, because it makes it sound like you're putting yourself on a little bit of a pedestal. How...
Semantics is like...
no, I had it and I've forgotten it now.
It's because I said semantics.
Particular.
Okay.
How particular you need to be with the way that you do things or your use of language and all that sort of thing. Like, you see a lot of people, a lot of articles, and especially things on social media doing it, they try and adapt what's being written in journals to make it accessible for everyday people, because not everyone can read a scientific article and have any idea what they're talking about.
No,
I struggle sometimes.
Well, I've been down rabbit holes before where I've gone like, I've just heard the term quantum and I'm going, I'm going to look up quantum physics, and then you read it and you're like, you read one sentence on Wikipedia.
And this was a bad idea.
Yeah, you read one sentence.
Mistakes were made.
Yeah, well, exactly. You read one sentence and then you only understand 3 of the words in that, and, if, and but, and it's like, the other words I have to now Google, and then there's a whole other article. Which, But with the massing. So how, if we start with, how does a black hole actually occur? Obviously, I assume it doesn't just appear.
No. So this goes back to the life cycle of stars. So originally, material in space would be clouds of gas and dust, and irregularities in how that's distributed. So basically, there might be a little bit more over here and a little less over here, and that sort of thing means that things will start to pool and collect because of the force of gravity. If something gets it's a bit more dense over here, this area's got more gravity, or not more. That's another incorrect way of saying things. Not more, but a stronger gravitational field strength over here in this particular area. Things will start to move towards it.
Just as a thing for people to, because obviously this is a podcast, it's audio, to help people visualize it, which is a way I think Brian Cox has said, which is your favorite person in the world, Josh.
It's just, I don't like, it's just, I don't like listening to him.
Yeah, that's fine. But one thing, a very easy way for people who are listening to understand is very, very layman's terms, is if you just think of a flat bit of paper, and then you put more weight on, say, a bit of paper, and it's on it's on 2 tables and there's a gap in the middle. You literally just put stuff on the paper and the paper will slowly fold. And where that paper then folds, if you put other objects that are smaller near that, on that fold into where the other thing is, they will fall down into it. And that's a really, really basic way of understanding why gravity kind of pulls things together.
It's it's likely to be, that's probably a model of what's going on, because we're a model being something in science that we use to represent something, likely imperfectly. Because people talk about the idea of space-time and the 4th dimension and all that sort of thing, which is where gravity comes in and all that sort of stuff. And obviously, we live in a 3-dimensional world, or as far as we can perceive, a 3-dimensional world, and that's not going to be that everything's on a single layer plane in which then space decides to fold and move, which is often the pictures you see of stuff where you see something and that that almost like checkerboard grid is like flexing and bending based on this. Oh, look, there's this big massive thing here and it's flexing and bending. But essentially, things will move towards generally something with a higher mass or higher density to have gravitational field that has a higher gravitational field strength, and that collects and keeps collecting and keeps collecting. Eventually all these gases start colliding and this, that and the other, and it gets small enough, dense enough and hot enough, the nuclear fusion starts to happen. So potentially lots of hydrogen atoms, or hydrogen molecules probably is more accurate to say, because hydrogen goes around as H2, will start colliding into each other and eventually start forming helium atoms. And then those continue and continue and continue and continue. And that's essentially the stage that our sun is at now. After a certain point, that fusion happens to a degree where you start producing heavier elements through that fusion, or essentially when we say nuclear fusion, the nuclei of atoms are fusing together to form new atoms of elements that are heavier, like hydrogen forming helium and then onto things like the carbon and oxygen, this, that, and the other. And eventually you end up starting producing heavier metal elements like iron, at which point the star essentially starts running out of fuel, because it is fueled by these nuclear fusion reactions, which we can talk about actually. I think we may have mentioned it before, but the whole like E equals mc squared equation. Mass is realistically, in a way, it's like a super concentrated form of energy. It's weird to think about. I don't want to go into it right now because I understand it. It's too complicated. But essentially, the sun is giving off huge amounts of energy in all directions at all times, right? So the energy is being released, so it is moving from the star to other places, and it's being released in the form of infrared electromagnetic radiation. So your infrared, radio waves, visible light, UV, gamma rays, all those sorts of things, which as light travel at c, the speed of light. And you've got an equation of E equals mc squared. So realistically, if all that energy from the sun is being emitted, the energy, and that, here we go. So the E in that equation represents the energy in the nuclear store, so the energy contained within the nucleus of atoms. So if the sun is releasing energy, that must mean that the energy in the sun, which is that E, is going down. C, the speed of light, is a constant. So that means the sun is actually losing mass.
Yes.
Which is a weird thing. When you're fusing atoms together, certain quirky things happen, which means that mass is lost. And that means that massive amount of energy can be released. That's probably way complicated, but
I vaguely understood that. So it's basically just the E equals mc squared thing. E is energy, M is mass, C is speed of light. So what you say is the C never changes to speed of light. So if the energy changes, the only other thing that can change is the M, which is mass. So if the energy ever changes, the mass has to change because the speed of light never can.
So if the sun is releasing energy to elsewhere, that means less is being contained in the sun, so its mass must also be reducing.
Exactly.
There we go.
That makes sense.
But essentially, and that's not actually really relevant right now. That's how stars work. That's how stars create lots of energy that we use on this planet for literally everything. But once you start producing these heavy elements, for example, iron, I think, is when it starts to really happen. The star starts to run out of fuel. It can no longer carry on those nuclear fusion reactions. So it starts to die. Obviously not death, but we call it, they start to die. Our sun is not large. It's probably a medium star, an average sized star. It will become a red giant, and probably all of the inner planets will be engulfed within it. After which it will become some form of nebula, and then probably recompact and form into a white dwarf while it still has a decent amount of energy to give off. And because those then nuclear fusion reactions are no longer happening still, it will eventually just start to dull and lose that energy and dull and become darker and dull down to become a black dwarf. And then it will that's it.
Right.
For much, much larger stars.
Because our sun's not even that big by comparison. No. People should go online and basically look at our sun compared to so many other suns. Because obviously our sun compared to the Earth looks gigantic. But when you actually compare it to some of the other stars that we know of in the known universe, it is absolutely minuscule compared to some of them.
We're tiny. The sun is not big. There's much bigger stars. Instead of becoming that nebula of sorts, they'll become a red supergiant. Lots of super in space, like supermassive black holes, supergiant. And then they'll go supernova and essentially blow up, which is literally like a massive. It's literally they explode.
Didn't we watch one? No, one happened recently. It was in the last year or so, I think.
Well, it reached us within the last year or so.
It happened millions of light years ago. But.
Well, no. There's another one. Light years is a unit of distance.
Yeah, as soon as I said that, I felt like an idiot because I was like, I know that because one light year is if you are traveling at the speed of light, it will take you 1 year to get there. That is a light year. So obviously, it being millions of light years away means what we're seeing right now because of the speed of light is of an image millions of years ago. So it, essentially looking back in the past. Because I think one thing, I don't know if we've mentioned in the podcast before, but I think it's like, if the sun explodes, or not explodes, but if the sun just disappeared, we wouldn't know for like 8 minutes or something.
Yeah, about that.
Yeah, so it's like, because we're actually looking at the sun is actually looking at what it was 8 minutes ago because of how long it takes for light to get to us. Yeah, cool.
Well, we are. Oh yeah. So red supergiant then explodes, supernova, and then again things start compacting. And relatively large ones will become a neutron star, which is still very dense and relatively bright. Normally has like almost like a 2 poles thing to it. It's weird. Don't know a lot about them. But the biggest of stars, as soon as they reach a certain size, will keep compacting, keep pulling in more mass, and eventually form a black hole. And a black hole's gravity, the strength of gravity that a black hole has is strong enough that it will even bend light, which is part of the things about light being a wave and a particle, is that gravity can affect it. So particle, it has mass of some kind. Very, 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 very small mass, but it has mass of some kind with like photons and stuff and all that.
It's weird that light has mass.
It behaves as wave in certain situations and a particle in others, and it's weird, bad juju. Light is bad juju. Done. Scientific explanation. There you go.
Done. We don't need
try
any
and
more science.
Disprove that hypothesis.
Yeah, we don't need any more science in this bitch.
No. And then they form black holes and they start bending light and start collecting things and becoming more massive and more massive and more massive, and their realm of influence increases. And up until now, pretty much all we've been able to do is observe the effects of black holes. We've been able to see things moving around a seemingly empty space. So black holes have been our hypothesis for an explanation of there's nothing there, but things are moving around it. It's like in episode 2 of Star Wars, where there's like, things are moving around something here, but there's nothing here. There should be something here. And there's like, oh, that's where Camino is. Black holes are like Camino. Except that like, we can't go there. And there's not going to be clones and people with really long necks and all that sort of thing. But basically, they're gaps in space that we can't see anything from. We can't detect anything from them. It's theorized that people have probably heard the term Hawking radiation, named after the late Stephen Hawking. But that's a theory of black holes essentially should be a perfect black body. In science, what that means is that they are a perfect absorber of all radiation and a perfect emitter of all radiation, potentially. Doesn't quite work like that, but the Hawking radiation is meant to be radiation that should be detectable because it is generated and emitted just before the event horizon. And the event horizon around a black hole is the point of no return. But we can't detect anything about them, yada, yada, yada. We can only see their effects, things orbiting around them, suddenly blinking out of existence after a short while, well, actually probably quite a long time. But all that sort of thing, we've seen the effects of them. The reason apparently why this picture is such a big deal is because they've collected enough data in terms of the image and coordination of telescopes and satellites and all that sort of thing. 5 petabytes of data, which is basically 5 million gigabytes, to create that one image to say, look, we actually have a picture that shows the event horizon. Like, we're seeing the very, very edge of a black hole rather than just these are the things around it that are being affected. And
I was going to quickly say for people, just because my only job here is to basically translate if some things are a tiny bit too complicated for people who may not be able to visualize it properly. The way I visualize an event horizon things is very, very simply, it's just like with that paper analogy I said before, the paper's kind of, say you have a flat bit of paper, you push down on the middle and the weight goes down. It's almost like at the edge of where it starts to go round. So as it goes down and goes from being flat to a dip and down, as you get to a certain point in that curve of going down, you can't ever go back up. That very, very layman's terms is basically you go down a certain point, you can't ever go back up. That's essentially how I understand an event horizon to be.
Yeah, more or less. There's plenty of videos you can look up where people have basically got some sort of circle and covered it, stretched over it like elastic and stuff, and put a relatively heavy weight a heavy mass in the middle. If you don't have this whole episode is just correcting my use of the word mass and weight. But you put something in the middle and it folds and dips and has that curvature, that curve that you would think about like, oh, that layer of space-time, whatever it is doing. And then they'll use something of much less mass, like a ping pong ball, and just push it so it's like going around. And that's just replicating then the orbit of, say, the moon around the Earth. Curvature in space-time, the effects of that gravity is what's keeping that ball in orbit going in circles. Mm-hmm. Kind of like all the little the coin in the side, and they go round and round and round and round and round and round and round. And once you get to a point, because it's relatively orbiting, once you get to a certain point, it's doing that thing right at the beginning, and then drops. Yeah, that's pretty much the event horizon. Oh, yeah, so it's kind of like that. Yeah, those things. Although the sound effect probably doesn't pertain much to that, but oh well. But this does kind of bring up the question about gravity and how gravity works, and this actually comes into Newton's laws of motion, which a lot of people can misunderstand and misinterpret. The first one is that, and doesn't hugely apply to the situation, but the first one is an object will continue moving at a steady speed in a straight line or remain stationary. So if it's already moving, it will continue moving at the same speed in a straight line, or it will not start moving if it's not moving, unless an unbalanced force acts on it.
Right, and what would like an unbalanced force?
So let's see, when you throw a ball upwards, the only force that's acting on it is going to be gravity. Mm-hmm. It's weight, because weight is the force due to gravity. So the ball's weight is the only force that's acting on it.
Yeah.
Because you're not inputting a force to make it continue going upwards. Mm-hmm. You've already provided it with that as you've thrown it, and as soon as it's left your hands, you're no longer giving it any force. You're not applying a force to that ball anymore. So what does that ball do as it rises? It slows down, because the only force is gravity going downwards, so that's unbalanced, so it slows down.
Yeah, because obviously if there wasn't the force of gravity, you would throw it up and it would just continuously go up until out of the atmosphere or whatever.
And then once it reaches that peak, it stops and then continues to accelerate, because it's technically been accelerating that whole time, because acceleration is just a change in speed. It then starts to accelerate towards the ground and speeds up and speeds up. So basically, if you have an unbalanced force, the motion changes.
Right.
If you don't, it stays the same.
Okay.
So let's say, for example, a bullet is moving very, very, very fast horizontally. Mm-hmm. Yes, it's going to curve as it goes down because of the weight due to gravity, because as soon as it's left that gun, the only thing that's acting on it is the force of gravity. Mm-hmm. But there's no longer a force propelling it, and the effect of air resistance is pretty much nothing. So until it hits something, it's pretty much going at the same speed the whole time. Mm-hmm. But it's just kind of curving a little bit. But it doesn't like slow down, really. Mm. There is a little tiny bit of air resistance, but not enough to be significant. So its speed, horizontally, doesn't really change. Mm-hmm. If that makes sense.
Yeah.
So there's no unbalanced force, because realistically there's no horizontal forces on it.
Yeah.
Its horizontal movement doesn't change.
Yeah.
That's Newton's first law.
Right.
The second one is basically the whole F equals ma, if you've heard that equation. No. You may recognize it.
Force equals mass acceleration?
So force equals mass times acceleration. Or basically saying that for an object of a constant mass, the force applied to it will be directly related to the acceleration that object experiences. Mm-hmm. Which applies to gravity because if you think about something like Earth, which has got lots of gravity, it's got very, not lots of gravity, I keep using this, lots of gravity, its gravitational strength is relatively strong, especially compared to like us or a ball or something.
Yeah.
So the force due to gravity is relatively large. So something with a small mass, no, this is bad, this is going really wrong. This is difficult to explain.
That's fine.
Basically, if you apply 100 newtons, say, of force to something to try and push it, something with lots of mass is not going to start moving as quickly as something with not much mass. So with the same force, less mass it speeds up faster. So the amount of force for something of a constant mass, the amount of force is something we call directly proportional to the acceleration. That is something to do with the gravity. So for example, the moon is constantly trying to accelerate towards the Earth.
Right. Things
mean that it doesn't start moving towards the Earth, but that's another thing. The third one people will definitely have heard of is the whole, if object 1 exerts a force on object B, then object B exerts an equal but opposite force on object 1.
Right, yeah.
So the forces are equal and opposite and all that sort of thing. But it basically means that if you push on the table, that table, or even just you, or let's just say you're standing on the ground, the force that you are experiencing, or the force you are exerting on the ground is, let's say you weigh 70 kilograms, so you're exerting 700 newtons on the ground. You're not moving through the ground, so you're stationary, so the forces are balanced, which means that then 700 newtons must be pushing up from the ground onto you.
Right.
So from the two objects, you and the ground, the forces, both the contact force of you on the ground and the contact force of the ground on you, are both equal in size. They're both 700 newtons, but they're in opposite directions. And that's the third law. And that applies to the fact of, like, if you say two objects in space, let's say you've got two tennis balls in space next to each other, they're going to move towards each other. One's not going to move towards the other. They're both going. The gravity works both ways, and they move towards each other.
Yeah.
In the same way, the force that you exert on the Earth because of your gravity is the same as the force that the Earth exerts on you.
Right.
Which sounds very, very odd because the Earth is much, much bigger. But if you jump up and then fall back down, your mass is very, very small. So with the same force, you're going to have lots of acceleration, which is why when you jump off a cliff or something, and this is dark places, if you dive off a diving board, there we go. You're doing the Red Bull challenge, you jump off the cliff into the water, there we go. You start falling quicker and quicker and quicker very quickly. At the same time, technically, the Earth is moving towards you.
Right.
But because the Earth is so massive compared to you, its acceleration is tiny and it's not really going anywhere.
Right.
So when there's two objects of significantly different mass, one's very, very small, one's very big, they both move towards each other, but the thing that's smaller moves much, much further because that acceleration is much bigger due to that second law that we talked about.
Yeah.
So the way gravity works between two distant objects is a combination of Newton's second and third law.
I see.
So the small thing, the less massive thing, I should say, moves much faster because it has less mass. So the same force has the much larger acceleration because it's still a constant mass. But the big thing still moves very, very slightly towards the small thing because the forces are equal and opposite but in opposite directions.
Yeah, I totally get it.
So it doesn't require, the whole equal and opposite thing doesn't require two things to be touching. Whenever there is a force, and that could be the force of gravity, the force of the Earth exerting its gravity on you, there is always an equal and opposite reactionary force, which could be the effect of your gravity on the Earth.
Yeah. So for people, I've got it. I understand what you're saying now. For people, I'll try and explain it in very layman's terms. Essentially, the Earth is very heavy. They're terrible. I've already started off terribly. Let's try that again.
Heavy is technically not the wrong word to use.
Fair enough. Well, the Earth,
but let's say it is massive.
Yeah, it has a lot of mass, and I do not have a lot of mass. So what happens is that I would then have to have substantially more acceleration than the Earth would have for it to be even, essentially. Like really, really basic. It's just that obviously I do exert some amount of gravity because I have a certain amount of mass, which is tiny. If I just said, for argument's sake, just for people to get really understanding a lot easier. For example, if the Earth weighed 1,000, let's just say, not even qualify it as anything, just 1,000 of something, okay?
Arbitrary units, done.
So the Earth weighs 1,000. I weigh 10, which obviously was ridiculous, but let's just say for an example. So to make those two, so the Earth's, if you said the Earth was 1,000, I was 10, I would have to have 100 acceleration, and the Earth would have to have 1 acceleration, because my 10 of my mass times the 100 acceleration makes 1,000. The Earth's 1,000 times 1 makes 1,000.
Because
that
the forces have to be equal and opposite.
Precisely. Because obviously, and it's hard to comprehend, but the main thing is that
when you can use the equations to see it, when you can see someone doing some sort of maths with that F equals M times A equation, everything starts clicking properly.
Yeah.
I think the main thing is getting your head around that the force that you exert on the Earth and the force that the Earth exerts on you are the same.
So I think I've got my head around of that. There's I mean, as I said, this science but simple, but we've got the sort of general ideas of how black holes work, some of the misconceptions around certain scientific wording, and mainly theory and hypothesis and that sort of thing, and weight and mass, and why the image of the black hole was not only so important, and a general idea of how black holes work. I will also premise and just say, I'll include a link in the description and stuff, that the first episode we did, I'm pretty certain it was, second episode we did rather, was about the sun and tides and the moon.
Yes, it was episode 2, because episode 1 was energy and light bulbs and stuff. Yes.
Exactly. So the second episode, we do go into a bit more detail about gravity and that sort of thing. But hopefully you've been listening to all of these episodes.
We'll probably go into much more detail in this one, because that second episode, I think we talked more about a bit about tides and stuff, and then we ended up on solar system stuff and a bit of orbits and things and all that. But this has gone into much more detail about how gravity is working in terms of interacting with things and two different objects working against each other.
Exactly. So if people are getting a bit confused about this and haven't listened to the other episode, I believe it's the episode 12 of Genuine Chit-Chat, and I'd say go back and listen to that. You get a general overview of gravity, and then come back to this one if you're having issues, or watch some stuff on YouTube. But we're getting pretty close to the hour mark now. It says flown by. Is there anything you want to add before we start basically wrap up?
No, I think I'm good. Just the idea that mass is the amount of stuff, weight is the force due to gravity. Two objects will both exert gravity, the force of their weight on each other. So, because even a person, you have gravity, you have a gravitational field, which is very, very small compared to, say, the Earth, but two different objects will both have a gravitational effect on the other. It's not one way, because of Newton's third law is opposite and equal forces, and that just means that they move at different speeds towards each other, or move at different accelerations towards each other.
Yeah.
And also, black holes are massive enough that their gravitational field will bend light and nothing can escape, and the point of no return is called the event horizon.
There we go. Nice.
Which is what the picture is of.
Yes, that's it was. Is the event horizon is the picture of the light bending into it. Okay. Awesome. Well, that's mind-bending. Hey! Sorry. Wonderful. Once again, Josh, it's always a pleasure to have you on. And we've got a couple of ideas for the next few episodes as well, so I'm sure we'll record them in the coming future. Perfect. Well, thanks, man.
I've still not been paid. Help me.
And that's the end of the podcast. Thanks as always for tuning in, guys. Just to clarify, all the episodes of Science But Simple I've listed in the description, but just in case you don't want to read and you just want to hear it, episodes 6, 12, 18, 25, 38 and 47 are all episodes of Science But Simple, which, as I said at the start, are the essentially mini-series of this thing. Hopefully, if that end bit didn't kind of melt your brain a bit too much, then you'll go back and listen to the other episodes, because, one of them's about climate change, one's about how light bulbs work, I think sea turtles are in one of them as well, so it's quite a wide amount of subject matter for Science But Simple, so, go check it out if you liked it. Anyway, coming up in the next few weeks, as I said, I think I've said it at the end of pretty much every episode of the podcast for probably the last 2 or maybe more months now. I've got the chat recorded with Beth Crane of We Fix Space Junk. I will be releasing that at some point soon. It's just that I've had other things popping up and I did good in English. I haven't done a Science But Simple in a while, so I thought it was a good time to sort of do one of those. Looking at my schedule at the moment, I've got a podcast planned to do on Tuesday, and then I've got another one planned to do the following Tuesday, so I'm not sure if I'll be releasing one of them or if I'll be releasing the Beth Crane one. I'm not really sure. If you have a preference, send me an email at genuinechitchat@outlook.com or on any of the social media things. Send me a message on Twitter, Instagram, Facebook, any of that sort of tomfoolery, and I will read them and respond. So if you do have a preference, if anyone is really clamouring for this Beth Crane chat and I'm just constantly teasing with it, then let me know and I may release it. Who knows? I don't even know really, because it just kind of as and when as the week comes makes me, depends on what the other sort of things pop up as well. But anyway, I think that's about it. I'm going to try and not keep this too rambly and stuff because it is currently midnight on a Wednesday night, so which I normally record these things on a Sunday, but it's a long weekend. I've got 4 days off and it's my girlfriend's birthday, so I probably should spend some time with her rather than spending the whole Sunday doing podcasting things. So trying to do stuff in the week because I'm such a nice person. Anyway, guys, as I always say, I really, really appreciate each and every one of you listening, especially to the end. It really means a lot to me. And the only thing I ask is, if you like this on social media and things like that, that's great. I appreciate that. Tell your friends, tell people you know and who may enjoy this and things. The back catalogue of episodes covers such a wide amount of subject matter with such an incredible amount of guests, all who are different and brilliant in their own ways. I feel like almost anyone could find at least one episode they'd enjoy. So, if you're a long-term listener, what would really help the show out is I haven't got a Patreon or anything at the moment, so I'm not asking for money. I'm not really asking for iTunes reviews. I mean, they'd be nice, but I know people can't really be asked for them, which is fine. But, mention Genuine Chit-Chat to people, get the word out, spread it. The podcast is slowly growing, but it can always use a bit more. And I just appreciate anyone listening and anyone sharing. So, yeah. Anyway, that's enough from me, guys. So thanks again, and I'll talk to you all next week.